Hello everyone, and welcome to our new book, Frogs, Fleas, and Painted Cubes, where we're going to be dealing with quadratic functions. And in the past, we used in prior units, we studied problems that could be modeled with linear and exponential functions as well as inverse variation. Well, in this unit, we're going to explore quadratic functions, and quadratic functions are found in many interesting situations, such as the height of a basketball or how high a frog jumps. You have been using the quadratic function in your life for quite a while now. You just may not have been aware of it. So we're going to learn a little bit about it here in this unit. So to begin with, our first learning target for Ffpc, as in Ffpc, frogs, fleas, painted cubes, Ffpc 1.1, our learning target is I'll be able to correctly describe the shape of a graph that represents the areas of rectangles with a fixed perimeter and determine which rectangle will have the greatest area for a fixed perimeter. Our ACEs for this first investigation is starting on page 14. It's 1, 2, 16, 17, and 33. We begin our investigation on page 8 called Staking a Claim and Maximizing Area. It says, suppose it is the year 2100 and a rare and precious metal has just been discovered on Mars. You and hundreds of other adventurers travel to the planet to stake your claim, much like the land rush in Oklahoma. You are allowed to claim any rectangular piece of land that can be surrounded by 20 meters of laser fencing. We want to arrange your fencing to enclose the maximum area possible. So to give you an idea of what we're looking for here, let me show you a video. It's not about Mars, just about fencing in general.
Okay, I've got to build a rectangle, and I have 14 meters of fencing. No problem. There we go. A nice 4x3 rectangle. Hey, Jay. It's Jay. Listen, I just built the fence over here at Site 1. I need you to make the same fence over at Site 2. You have the same amount of fencing, 14 meters, right? Right. I got 14 meters of fencing here. Okay, get going, and I'll be over later. That should do it. A perfect 6x1 rectangle. Hey, Jay, what's this? It's a 6x1 rectangle. Isn't that what you built? Nah, my fence is 4x3. Well, at least they have the same perimeter. Yeah, but they have different areas. Is there another rectangle with a perimeter of 14 meters that has a greater area? Which rectangle will have the greatest area for a fixed perimeter?
Okay, so that's what we are looking to find out here. It says, what are dimensions of a rectangle with the greatest area for a fixed perimeter? Remember, we're dealing with 20 meters of laser fencing, so that's going to be your perimeter, the outside measurement. As we look at the bottom of the page for problem 1.1, we start in part A. Number 1 says, sketch several rectangles with a perimeter of 20 meters. Include some small areas and some with large areas. So I've given you a couple of examples here. We could have one that is 1 by 9, because 1 plus 1 and 9 plus 9 totals 20. Okay, 1 plus 9 is 10, times 2 is 10. We could also have a 5 plus 5 is 10. That's two sides. We know we have the other two that are the same, so that's 20. Again, 9 plus 1 is 10, so we know 9 plus 1 is 10, and 10 plus 10 is 20. So I want you to give me some other examples of rectangles we could create with a perimeter of 20 meters. Parts 2 through 4. In 2, it says make a table showing length, width, and area. So you should have 3 columns in your table. And for every rectangle possible with the perimeter of 20 meters. So not just the ones that you gave an example of back here. I want every single one, okay, that have whole number side lengths. So we don't want to have anything that's 2.5 by 7.5. Okay, we want all whole numbers. Then describe some patterns that you observe in the table. Once you've done that, make a graph of the data with length and area, and please describe the shape of the graph. So how does the pattern in the table appear in the graph? How do you see that relation going there? And then we jump into B1 and 2. What rectangle dimensions give the greatest possible area? So we want to see what the greatest possible area is. Please explain how you know that, and then determine if we said the dimensions were not restricted to whole numbers. So if we could do the 2.5 by 7.5 or whatever other non-whole numbers you want to use, would this change your answer as of the size that of length and width that has the greatest possible area? And please explain that. So that is investigation 1.1, and our ACEs work again is beginning on page 14, 1, 2, 16, 17, and 33. Look forward to seeing your questions in class.